Hello. In this video, we'll make a space-time diagram of length contraction. On the left here, we see a blue reference frame with an observer, say, on the ground with the frame attached to the ground, which we label the K-frame, or the stationary frame, using Einstein's notation. And this frame has a vertical spatial coordinate y and a horizontal um, spatial coordinate x. To the right, we see the K-prime frame, or the moving frame, moving with speed v with respect to the K-frame. And this K-prime frame is moving at 50% the speed of light, with a ruler lying along its horizontal axis. This K-prime frame also has a vertical and horizontal coordinate, y prime and x prime. To make things easy, we'll assume that the speed of light is equal to 1, which means that the speed here of the ruler is simply 0.5 meters per second. Next, we want to create a space-time diagram for a reference frame K, and we just simply plot x versus t, our horizontal displacement versus time. Typically, we should be plotting x versus ct, but we're assuming that c is equal to 1, therefore we'll just plot x versus t. The idea is that in a space-time interval, x and ct shows up. Sorry about that. At t equals 0, we'll assume that the observer in K sees the ruler, in which case the ruler would just lie on the x-axis and have a length L. Since the speed of the ruler is 0.5 meters per second, 0.5 meters per second, we can write it as 1/2 meters per second. Or in other words, the top end of our ruler is tracing out an evolution on our space-time diagram with a slope of 1/2. That is, the top end of the ruler is moving such that it moves up 1/2, up 1/2. And connecting the dots, we see the evolution of the top end of the ruler. The bottom end of the ruler would entail the same thing. The bottom end of the ruler evolves also in x and t, and its slope is up 1 meter over 2 seconds, up 1 meter over 2 seconds, and so on. And here I draw the ruler again at some arbitrary point in the future. These two diagonal lines are sometimes called world lines by physicists. Here we have what's called relativity of simultaneity, namely at this time capital T in green, the ends of the ruler correspond to the positions A and B at the same time. We have simultaneity of the ends of the ruler corresponding to positions A and B at the same time. But when we look at the K prime frame, we'll see that this simultaneity is lost. And this is a general feature of the special theory of relativity. Simultaneity in one frame doesn't necessarily imply simultaneity in another inertial frame. Let's make some room here and plot x prime versus t prime on top of this graph. And to do this, we can make use of a clue. Notice that when t is equal to 0 in this graph, that corresponds to the x-axis. The x-axis corresponds to t equals 0. This means that the x prime axis corresponds to t prime is 0. The x prime axis corresponds to t prime is 0. So I have my t prime is 0 implies my x prime axis. And I'm going to use the Lorentz transformation to find the slope of the x prime axis. And you recall that the Lorentz transformation is simply t prime is t minus vx over square root of stuff. I'm ignoring the division over c squared because I'm assuming c is equal to 1. T prime is 0. Therefore, I can write that the ratio or the slope of x versus t is simply 1 over v. Notice here that v is 0.5, so the slope is 2. And the second thing to notice is that we have a discord here. X over t is meters per second, but 1 over v is seconds per meter, it seems, at first glance. The reason why there's this discord is because we set c equal to 1. If we put in the c's, you'll see that things look just fine. And here's how it looks putting in the c's, in which case now it's dimensionless on both the left and right side. But the end result would still be 2. This means that when we graph our t prime axis, to plot its slope being 2, we go up 2 over 1, up 2 over 1, up 2 over 1, and connect the dots. And I'll use the color yellow for the primed coordinate system, or my K prime frame. And now we want to find the t prime axis, and we go through the same story. And notice that For the t prime axis, we can use our blue graph again as a clue. Here in the blue graph, when x is 0, that corresponds to the t-axis. When x is 0, that corresponds to the t-axis. So therefore, that would imply that when x prime is 0, that should give us the t prime axis. And then writing down the Lorentz transformation, x prime is x minus vt over square root of stuff. And noticing that x prime is 0, we get that the slope of the x prime, of the t prime axis is x over t is equal to v, and v is just 1/2. Okay. Therefore, when I come to my blue graph here and I plot in yellow the t prime axis, the slope is up 1 over 2, up 1 over 2, and then I just have to connect the dots. But notice it coincides with the world line of the bottom end of the ruler. The t prime axis corresponds to the world line of the bottom end of the ruler. Next, we want to place the ruler in the prime coordinate system, or on our yellow coordinate system here. And that ruler has a length L naught, the rest length, and it should lie along the x prime axis when t prime is 0. But the question is, how long do we make it? Well, we have a clue. We have these two world lines of the top and bottom of the ruler. And this top world line, it serves as a boundary for the evolution of the ruler in the k prime frame. Therefore, I know that when I sketch the ruler in the k prime frame, it should be sandwiched in between these two world lines along the x prime axis as such. And it has, again, a length L naught there along the x prime axis when t prime is 0. Next, we want to evolve this ruler and notice that in the k prime frame, the ruler is not moving. It's just sitting there with the left end attached to the origin. This means that the parts of the ruler, or for example, the bottom end of the ruler, it just ages with time along the t prime axis. And the top end of the ruler also just ages at the same position L naught. It just ages with time parallel to the t prime axis here. Let's have the top end of the ruler correspond with position A, and we need to find where the bottom position corresponds. It looks like our ruler is over 1, up 2.5 for the yellow ruler. Therefore, I have this sort of a depiction for the yellow ruler where the top end corresponds to position A, But notice the bottom end does not correspond to position B. Okay. This means that we have simultaneity for our blue ruler. That is, the ends of the blue ruler correspond to positions A and B at the same time, capital T. But our yellow ruler, its ends do not correspond to positions A and B at the same time. Now notice I say corresponds to. It's not that it would be at positions A and B. Keep in mind that the unit steps along the x prime axis are different than the unit steps along the x axis. So again, simultaneity in one frame does not imply simultaneity in the other frame. And notice that each point of this ruler along the x prime axis corresponds to the same time. T prime is 0. To try to appreciate what the grid looks like for x prime versus t prime, notice that the line of simultaneity for the k prime frame, these lines run parallel to the x prime axis. Say, for example, from 0 seconds, 1 second, 2 seconds, 3 seconds. And the lines of a constant position, the lines of constant position would run parallel to the t prime axis. In effect, we have what appears to be a distorted grid in the k prime frame. If we had drawn the xt graph on top of the x prime t prime graph, we'd have the same thing. The grid for the xt coordinate system would appear distorted. Because in that case, the k frame would be moving to the left with respect to the k prime frame. I hope this was helpful. Here we see that Lorentz transformations allow us to draw the moving frame on top of the stationary frame, the k prime frame on top of the k frame. And furthermore, it helps us visualize the lack of simultaneity between one frame and the other.